Hello everyone, in this video I'm going to go through 4 problems that we have in chapter 5, and these are network modeling problems. In the previous class we covered and we introduced 4 types of network problems, and these are the transshipment problems, shortest path problems, generalized network flow problems, and then the maximal flow problems. We're going to start with the transshipment problem, and here we have an example of a German manufacturing company that produces cars, and they want to get their products from one location in Germany, which is, if you see it here, which is from Hamburg, that's northern of Germany, to Jacksonville, Florida. That's the one of the places. The other one is Newark, New Jersey. All right, so these are 2 different receiving or ports where these cars can be shipped to, and then from there the cars are supposed to be delivered to Boston, Massachusetts, Columbus, Ohio, Atlanta, Georgia, Richmond, Virginia, and Mobile, Alabama. So some parts in the east of the United States and some parts in the south. And that's how it looks like. So we're getting stuff from Germany, we're getting cars from there, and that's going to go to Newark, New Jersey, and Jacksonville, Florida. And from there we need to deliver these cars to these locations of demand. So we need those cars to be delivered there. Now, currently, there are 200 cars that are available at the port in Newark, and 300 are available in Jacksonville. So there have been some cars that were delivered from Hamburg to these 2 places, and we have 200 cars there in Jacksonville, in New York, and 300 in Jacksonville. And that's how the network starts. We denote this by minus. So when we say that minus 200 Newark, 1 is the node. So that's the node number 1. And 300 at Jacksonville, this means that we have, that's a minus, this means that we have products that are there. I know that it's counterintuitive, we talked about it last time, but this is how it is in network modeling, where we have the plus numbers are demand, the minus are supply. So basically we need to get rid of those, okay? And these cars should be delivered to these places, and these are the these are the needs here. Like you have Boston that requires 100 cars, Columbus that requires 60, and so on. So now for each one of these routes, there is what we call arc. This is called arc. So this arc, this is the delivery, the unit cost delivery. So the delivery of each unit is going to cost us $30 from Newark to Boston, okay? And on top of each node, the node can have also the name of the place. We have Boston here, New York there, Richmond there. We got also the number of the nodes. So 1, 2, 3, 4, 5, 6, and 7. We have 7 nodes in total. The numbers highlighted in yellow, these are the supply numbers because they're minuses, while the blue ones, blue highlighted numbers, are demand. So we need to get those 200, 300 to all these places, right? Now, can we do this? This is the first question we have to ask. Can we do this? We have about 500 cars that should be delivered there. If we have the quantity less than the demand, this is one of the problems. We have 3 situations where we have the supply, the demand more than the supply, and where they are equal to each other. And for each one of these, when it comes to constraints, we do the modeling slightly different. But let's translate this into our Excel sheet. We need to start with this. We have what to be shipped, right? The number to be shipped. From where? That's the node. This is basically the node number. And just for the sake of labeling, let's say from city to another city. And what's the delivery cost? So unit delivery cost. And then we need to fulfill the demand here. So we have this is going to be the way we do constraints in network modeling. So we start from node, and then after node we actually have the left hand side. So the left hand side here is referred to as the net flow. So we should say that if I have minus 200, I have to deliver all of them. This has to be fulfilled. Minus 200, and then right hand side. Oh, sorry. This is net flow, while the right hand side is the supply or demand, depending on what we are talking about. Or this is either supply or demand. All right, how many nodes do we have? We have 1, 2, 3, 4, 5, 6, and 7. All right, so the number of cars to be shipped from where to where, that's the problem. This is what we're trying to do. We're trying to minimize the delivery cost here as much as we can by deciding how many cars to be delivered from where to where. That's the transshipment problem, basically. So we have a route from node 1, and that is, well, if I want to be a little bit more specific here, I would call this in Newark to from 1 to 2, Boston, and the unit delivery cost is, as we can see, from 1 to 2, that is $30. All right, and then here, that's the decision variable, right? Remember? Now, then we have from 1 to 4. From 1 to 4. And again, this is from Newark. This time it's to Richmond. And the unit delivery cost is $40. So $40 per car. All right. Now, next we can start with 2. So 2 to 3. 2 to 3. And then we've got 3 to 5. And then we got 5 to 3. We've got also 5 to 4 and 5 to 6. There are 3 possible deliveries from 5 to 6, right? We've got also 6 to 5, and then we got 7, we got 3 7s, 7, 7, 7, 7 to 6, so starting from the lowest, 7 to 5, 7 to 6. I should have started with 7 to 4, 7 to 4. So how did I write these ones? I just started one by one. So we started the flow from 1, right? So we've got from 1 to 2, 1 to 4, and then I proceeded with 2 to 3, and then from 3 we have 3 to 5. Now the next is from 5 to 3, and then 5 to 6, and 5 to 4. These are 3 5s. And then from 6 we have 6 to 5, and 6 to, that's only the only one, 6 to 5. And then we've got 7, and that's basically because it's Jacksonville where the other port is. So from 7 to 4 and 5 and 6. Okay, so I'm gonna proceed with the typing the names of the cities real quick. Columbus, and from Columbus to Columbus everywhere here. And then we got 4, Richmond, and then we have 5, which is Atlanta. And so this is going to be copied and pasted everywhere where we have 5. And then we've got Mobile, number 6. Number 3 is Columbus, and then 6 is Mobile here and here and here. And then finally we've got Jacksonville, and that is copied, paste. Now from 1 to 7, can also add that just to be clear what these nodes are. Can add the node number and the city just to know what we're talking about here. So Newark, Boston, Columbus, and then number 4 is Richmond, 5 is Atlanta, and then number 6 is Mobile, and then Jacksonville. All right. Now, with that, we have complete, but we need to fill out the unit delivery cost. So we got 30 and 40. The next one was $50, and then from Columbus to Atlanta was 35, and then from Atlanta to Columbus was 40. From Atlanta to Richmond was 30, and then from Atlanta to Mobile was 35. Then from Mobile to Atlanta is 25. Jacksonville to Richmond is $50. It's a little bit more expensive, and then to Atlanta is also 45 and 50 here. Okay, so these are all the possible routes that we have with the cost of delivery. And what we're trying to do is to decide how many cars should be delivered from 1 to 2 and across all these routes in a way that we minimize the total cost. Now let's get to this part, starting with the right hand side, which is easier because if you guessed it, well, the right hand side is the nodes. So this is where we put these numbers that are highlighted. I'm gonna add the constraint color here. So this is going to be added manually. So we've got here minus 200. We got minus 200 here in at Newark, and at Jacksonville we've got minus 300. Now I'm going to explain why these constraints are not actually necessarily going to be fulfilled, all of them, because of the fact that our demand is less than the total supply in this case. So we're going to have more cars that are not sent from Jacksonville to, or from Newark to all the others. So I'm going to get to that part later, but all we need to here is just basically to add what node has what kind of demand or supply. So Boston requires 100 cars. Columbus requires 60 cars. And then Atlanta requires 170 cars. That's Richmond. Richmond requires 80 cars, 170 cars to Atlanta, and 70 cars to Mobile. Okay. Now, if you make a quick calculation of the demand, so the supply is all the minuses. So this plus this, that's the supply, right? That's 500. The demand is this number plus this plus this. We can do the sum instead if you want to be quick. So you see the demand is less than the supply. So we have 20 cars that we're gonna have left over. We can't deliver that. Okay? Now we're gonna get to this point later. But now what about the net flow? The net flow is basically what would be the result from each node. If we deliver from here to here, what would be the remaining here? Let me start by this. We're focusing here at nodes, remember? So what is leaving each node here? What leaves node number 1 are 2 arcs. An arc that goes from Newark to Boston and from Newark to Richmond. And these are minuses. So we're delivering 200. So this is going to be minus whatever that is shipped from that node. We have node number 1. Whatever that is shipped from 1 minus the other, because that is a minus. Remember, this is a minus. And then if we go to 2, at 2 here, we have only one arc that leaves Boston. So from Boston to Columbus. Now from Boston to Columbus, we have it here. We can see that this is the only arc that leaves this node. And it is, again, if it leaves, then it's minus, right? If it leaves it, if it goes from that node to the other, so if it doesn't receive it, that is minus. But we also have another one here. We have from Boston. From Boston, we have something that is coming to the node, which is plus. Okay, we're adding plus coming out of Newark. Okay, this is coming from Newark to Boston, from Newark to Boston, coming to 2. So that's plus minus what's leaving Boston. Got Boston leaving to Columbus. All right. Now, next is what leaves and comes to Columbus. What comes to Columbus is coming out of Boston. So we have plus coming out of Boston to Columbus, and we have another plus coming from Atlanta to Columbus, but we have minus leaving Columbus itself. Okay, and that is 1, 2, and 3. Coming to Columbus, leaving Columbus. And then we have Richmond, and Richmond we have 3 only incoming flows are pointing towards them. So this means that we have all in plus. Again, coming out of Newark, coming out of Atlanta, and coming out of Jacksonville. So basically, whenever we see Richmond here, we should add that. Richmond as a receiving city plus Richmond, we should be good here. And then when it comes to Atlanta, again, Atlanta is the most complex one. We have about 1, 2, 3, 4, 5, 6. So we have 6 arcs that interact with Atlanta. We have 3 pluses and 3 minuses, basically. So anything that leaves Atlanta is minus. So minus, minus, minus. Anything that goes to Atlanta is plus, 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 and then plus. Anything that goes to Atlanta is plus. Okay. Then we have Mobile. Again, anything that leaves Mobile, we have only 1, that is minus. Anything that goes to Atlanta is plus. We have 1 and another. All right. Finally, Jacksonville. We have 3 arcs that leave Jacksonville, which makes it basically 3 minuses. So minus, minus, minus. So what is it that we did? Just what we did was just the calculation of a net flow. So I have a quantity leaving Newark, another one leaving Newark towards Bridgemont. I have to count that as minuses because I'm losing that number of cars. This is why in the first place we have supply as minus. All right, so what is it that I want to calculate out of this? Remember, it was about the total cost, right? The total cost. So what is the total cost? What is this gonna be? This is gonna be green. This is our objective function. Well, these are the number of cars that will be decided by solver later on. I want these to be decided so that I minimize the total cost. So this is going to be the number. If it decides to ship, say for instance, 80 cars from Newark to Boston, then 80 cars times $30, that's the delivery cost for that specific route, right? So it's going to be this number times the corresponding cost of delivery, and then the next one and the next one, which reminds us with using sum product in this case. So we have all these quantities should be multiplied by and summed using the unit delivery cost for each corresponding route. And then we click OK and we get that. Now here is the trick. As the number of supply, the number like in the receiving, okay, this is, I just want to talk about this before I get to the how to do this using Excel, which is what matters. From a modeling perspective, we use X, I, J, and we did that before. I is the origin and J is the destination. So from node I to node J, basically. So that's the number of cars to be shipped or flowing from 1 to 2, right? So for example, X1, 2 in this case would be the number of cars to be shipped from node 1, which is Newark, to node 2, which is Boston, right? And this is how it looks like. This is going to be the number of cars that we're talking about, this cell right here, okay? And that way, the number of arcs determines the number of variables, all right? So each arc has number of cars, certain number of cars, even if that gets to become 0 after in the final solution, but it's a variable that should be counted. So in this case, we have about 11 variables. And then we use sum product to calculate the total cost. So 30, that's the coefficient, which is the cost for delivering each car from Newark to Boston, and so on. The constraints, and that is the net flow that we talked about. As I told you earlier, we have three types of problems here: when the supply is more than the demand, when the demand is more than the supply, and when the total supply equals total demand. In our case, the supply was more than the demand, as we calculated here. We have 500 cars, but the demand is for 480 cars. When we do this, here's what happens. The outflow, so the inflow minus outflow. Inflow, by the way, these are all the arcs that go into a node. So this is an inflow to Boston, but it's an outflow from Newark. So when we get at each node, there's an inflow and outflow. So at Newark, for instance, the inflow, we had only outflow. They're all minuses. They just they got out of that node. But let's talk about Boston. In Boston, we got an outflow from Boston to Columbus, but it's an inflow. There's an inflow coming out of Newark, right? So this has to be greater than or equal to supply or demand in this case. So in this case, that's the demand. So we need 100 cars there. Whatever that we get from Newark, let me go back there, just showing whatever that we get from Newark, let's say that we're gonna get, I don't know, 300. 300 will fulfill this, because if I get 200 only from here, if I get 100 from here, that's gonna fulfill the demand here, and nothing is going to proceed to the next. So at least 100 should be fulfilled here as a total from the inflow and outflow. Things will get clearer once we get to that point. So let me go back here. I don't know if I can use so I have 200 cars, and let's say that the model decides that we have to deliver 200 to this point. The node here, we are going to use at least 100 to fulfill the demand here, and 100 can proceed to Columbus. It mightn't proceed, but the model can use it towards the next node. All right. Now, the implication of this, when you have the supply is more than the demand, has a modeling consequence. So if I want to come back to solver here, for instance, what we're trying to do here, we're trying to minimize, right? So we want to minimize the total cost by changing those decision variables. And then the constraints are the net flows in this case. Just because this is a situation where we have supply more than demand, the constraint should be fulfilling all these numbers. So it has to be greater than or equal to the right-hand side, supply or demand, all right? So I'm gonna put equal and use simple linear regression. So if you see here, well, we managed to deliver to Jacksonville, or out of Jacksonville, 280. But that's fine because the minimum was 300 minus 300. So it was greater than or equal to. So we couldn't fulfill this, or we couldn't use all the cars, but that is why we had this constraint with that relationship. So we said greater than or equal to instead of less than or equal to make sure that we're fulfilling all the demand. What matters here now is the demand. We want to fulfill all the demand, right? And that's it. That's what we got. And the interpretation of this is that we have 120 cars that's going to be delivered from Newark. So going back to 100 is going to be delivered from Newark to Boston. So 120. We need only 100 here. So probably 200 is going to go towards Columbus from Newark, from Boston to, here, 220. So 100 was used at Boston, 20 proceeded from Boston to Columbus. Columbus requires 60, so that covered 20 out of the 60, and so on. So we don't need to think of the complexities. All what we get out of this really nice way of modeling this is that we can decide how many cars to deliver to where, so that we minimize the total delivery cost, basically. And that is the transshipment problem.